it wasn't that long ago that I was sitting in this room exactly where you are. All right, I'm a graduate from Temple. My first class was when this building opened, 1978. So I hear you. I feel your pain. All right, I know what's going on, at least getting to know what's going on. But the idea of this class, and let's just go back, and again, you said, hey, I'm in pre-calc, man. I haven't seen a derivative, an integral, whatever. The idea, and what I hope to get across, is that this means something to you, because it really does. It's the language in which we use to describe these physical objects, the mathematics. The nice thing about the mathematics, really, is that I can sit here and I could build all kinds of circuits with these capacitors and these inductors, but that's not the way you do it. You have to come up, you're usually given a design problem. So I'm going to say, look, I need you to build a laser pointer or something like that. So then you have to spec. It has to fit in the palm of the hand, so I have to start sizing up sizes of inductors and capacitors and stuff. But you don't go out and just start building it. You can. The nice thing about it is these guys can be described mathematically. And you know what's amazing to me? It's pretty damn accurate. I mean, really accurate. So with the mathematics of understanding what these capacitors and inductors and laws of motion, fluid flow and all that, it means something. Because now I can sit down and use a computer or pen and paper to start solving the problem first. Do a design. At least get me into a ballpark before I go out and start sizing all these things up. And again, I tell you, I've been teaching the freshman class for 4 years now, and then I taught it back and all that stuff. The most important classes that you have for the first 2 years are what? What do you think they are for the first 2 years? Take a guess. It's your math classes. It really is. Because if you don't pass your pre-calc or your calc on the first go-round, you only have one more shot at it, right? I mean, that's it. And if you don't get it the second time around, your math career is effectively over at Temple University. All right? So it's important, really, I can't stress you enough. When I was an undergrad here, they had the Math Science Resource Center. Actually, it was over in physics at that time. I would live in there because I had graduate students in physics that could help me with this stuff. I was no rocket scientist when I came out of high school in Chester, Pennsylvania. Believe me, I was fortunate enough that I think I had up to trigonometry, but I had no pre-calc stuff and all that. And here I am, basically thrown into the pool without learning how to swim. So you have to get the help around you to learn how to do this stuff. And really, I'm sincere about this. You have to go out and find the resources. Peter's probably a great resource for helping you. Use them, all right? Use a Math Science Resource Center. It's important. And if you get in trouble in one of those math courses, make sure you come over and see me or see an advisor, all right? Because, again, if you want to stay on this engineering course, you've really got, it's it. I mean, you got to just say, I've got to do this. I've got to get this down, all right? It's important, all right? I even have students that I mean, don't, I should probably turn the recording off, but I'll let it go. I'll say, go take it to community college. Take it to Montco during the summer, or to, you know, where you can. Because if you don't do well there, we never see it. It never hits your Temple record. And if you do well, it transfers in and then you move on. So if you find yourself getting into trouble in it, there's different alternate routes you can take. All right, but there's still, the root is you still got to go down the path somehow, whether you're diverting it and doing whatever. So it's important. I understand really where you're coming from. It was, for me, it was, I had to literally spend hours in that Math Science Resource Center. What was nice is I had people right there. I didn't have to sit at home scratching my head about this dot product or this chain rule or something like that. You've got those little troughs out there. The horse has got to go to the troughs, okay? So it's important. Come see me. I live up in room 708, all right? So I'll be glad to see you guys. I'll see you around, all right? All right, the way I like to do this is I like to talk to you about it, and I like you to ask me. So if there's something that's going to go on up here, again, I'm coming in today understanding that you did do some integration. Is that right? I mean, you could do the integral of sine of 8. Can we? Let's just, and really, there's only a couple of integrals that you have to understand. If I have the integral Anybody have any idea? Yeah.
Isn't it negative cosine
Minus, what about, yeah, minus cosine
and then whatever down the
of AT, and what happens to the A?
it goes to the front.
And is it out front or 1 over A? All right, is it that? Okay, just checking to make sure. What do we have? 0 to T. The integral of the cosine of BT. Sine, go ahead. Sine of BT, and what happens to the B? All right. We're going to be, all right, how about the integral of e to the ct dt? That one. Go ahead. Well, this is a C. It goes to the front, but it's 1 over C, e to the ct. All right. Go over here. Let's do this. Integral of t squared dt. Do we do this one? Go ahead. How about just let's do the integral. Let's start off with just the integral of dt from 0 to t. That's the most simplest one. No? Not happening? Huh? Yeah, just t. All right. Let's do the integral of t dt. Yeah, 1/2 t squared. Integral t squared. 1/3 t cubed. Yeah.
I was going to say t cubed over 3.
Yeah. T cubed. But these are the only ones you really need. That's it. So if you have these down, you can solve every problem in chapter 9. That's it. That is it. Really. I'm not kidding you. It's as simple. So just making sure that you understand this rule. You may not understand all the details of where this came from to get to here, but right now we're just going to apply this to this stuff, okay? Believe me, when I like to lecture, I like to have a discussion with you, so don't at any time feel intimidated that you don't want to raise your hand up, all right? Because I can always tell by the looks in your eyes that you're getting it or you're not getting it, all right? I've been at this business long enough, all right? So don't hesitate to ask, all right? Believe me, don't think that I don't understand this. Yeah, guess what? 90% of you are going to probably need help too, all right? So ask the questions, all right? But really, to get through this chapter, that's it. That's all we need, really. And that's the way I like to do this is problems. The only way to get through the mathematics, and when you take your electric circuits, your statics and dynamics, is to do problems. When Michael Jordan went out before a basketball game, what do you think he did an hour or 2 hours before the basketball game? Shoot the J, right? Shoot the J. Because what are you going to have to do during the game? I got to shoot the J, all right? So you make sure, it's practice, so you got to go out and practice. And that's what we're going to do in here, and hopefully you'll be doing that with Peter in recitation. So it's practice. The more you practice, the better you get, all right? My goal next year is to have my golf handicap below 10. So what do I got to do? Hit balls. Lots of them, all right? Lots of balls. I'm going to go through gloves. Gloves every 2 weeks. I'm going to burn holes in them. I'm going to hit so many balls, all right? We'll get there. We'll get you through this, all right? So that's our goal. All right, now, if you cut me open, you'll find electric circuits in here. So we're going to be working with these integrals and through the electrical engineering part, all right? So again, if you're in mechanical engineering, it's the same mathematics. It's just different applications. Capacitors, and we're going to do this just with capacitance and inductance, all right? These are very, very useful devices. I'm going to show you some videos. I'm going to show you some history of where this stuff comes from, all right? This is all on your blackboard, all right? So you don't have to write. Whatever you see up here is on Blackboard in a PowerPoint, okay? But I will be working on the boards over here, working out problems for you, all right? So we'll use both. But our discussion of this integral is going to be what's happening with two parallel plates and a voltage source, all right? So this could be a little battery like in here. And this is just two parallel plates. These parallel plates, typically, they're metal. These are metallic. And then inside of there is usually like a ceramic material. It's a non-conductor. And what we call that, it's a dielectric, all right? It just won't conduct electricity. So what we're doing here is now, I have a positive charge here, and I have a negative charge here. And I'm just holding them. What do they want to do? They want to get happy, right? Right? They want to go together. But now just think about this. I've got positive charge here and negative charge here. They want to get together, right? There's a force, right? Coulomb's law. And what's holding them apart? That dielectric is holding them apart. So now what I have are two charges that want to get together, but they can't. But now what we've set up is an electric field in there. That electric field, believe me, can do work for you. Capacitors can do work. So now I'm going to show you how a flash camera, that's how flash cameras work. They have a capacitor sitting in them, all right? So the idea here is we're going to be able to use this separation of charge, and then I can pull that charge back and use it to do some work for me or for something, to do something, all right? So it's two conducting plates separated by an insulator, or what we call is a dielectric, okay? And again, what you have is some type of battery, which gives us an electromotive force. So I can have, and this is the positive side of the battery. I will have, charges will migrate, and this plate will become positively charged. The negative side of the battery, this plate becomes negatively charged. Yeah?
What differentiates a battery from a capacitor?
A battery can give you constant power, and it supplies energy. A capacitor is what we call a passive element. So basically, I can store energy on a capacitor, but you'll see in a minute when I even get to the flash camera, the reason we use a capacitor in the flash camera is because the battery can't give you that big instantaneous amount of energy that you need to flash the bulb. It can only give you a little bit of energy at a time. So what we do is we charge up a capacitor, and that's when you're sitting there with your camera, and you'll see usually a little light flickers, and then when it goes constant, that capacitor is charged. You then depress the button, the battery goes out of the circuit, the capacitor comes in the circuit, and then flash. You dispense a whole bunch of energy. But again, that energy is dissipated, whereas in a battery, you're just getting a constant amount of energy out of it. Okay? We'll get to it. Good question. Very good question. So now what we're going to have is a battery just charging it up, and then we can come back and use that. So here's typically, you got to be careful with capacitors. I worked in a lab once, all right? And here's an interesting, screwdriver's missing, transistors are missing. I'm like, man, somebody's coming over and taking stuff off my desk. So what do? I take a nice 100-volt capacitor and charge it up. Put it on the desk. Let's go get a little drink of water, go over and shoot the scene, whatever. Next thing you heard this loud scream. And I knew exactly who grabbed the ends of the capacitor. Because all that energy went into burning their hands. So, gotcha. All right. So the idea here is you'll see these now. This does not look like two parallel plates to you, right? You're like, oh, whoa, wait a minute here. This thing's supposed to have two parallel plates to get that energy on it, all right, to separate those charges out. What you can do is, in order, again, we're going to see that the capacitance is going to be a function of the area and the separation of distance here. Capacitance is area divided by distance. I make the distance smaller, the capacitance goes up, and I make the area bigger, the capacitance goes up. All right? So what you can do is you can take, now again, you can use metal foil instead of steel. I can use like aluminum foil type of thing, use metal foil, and then have the dielectric sitting in between it. and then I could roll it up. Instead of having a big sheet that's like this, I put the foil on one side, the foil on the other, I throw the dielectric in the middle, and I twist it up like a doobie. Okay? Like a spleef, man. All right? So you just twist it up, and you're all ready to go. All right? So what that allows me to do is to take something with a large amount of surface area. When I'm manufacturing this, and I got to put this in some electronics where you want it nice and small. So you want to take something with large surface area and then shrink it down. So here I'm going to have a negative terminal. Here I'll have a positive terminal. I roll all this stuff up, and I stick it in a nice little insulated aluminum can, and I'm good to go. All right? The flash camera, there it is. Gotcha. All right? So now what you have is basically, here's a camera. All right? Camera has down in here, usually you have there's some printed circuit stuff. There's a battery that goes into the back here. Here's your flash head all the way up here. What you want to do is to get the energy from the battery out to that flash head. But the thing is, that battery may only be putting out milliamps of current. And that is not enough to get that thing to give me a nice instantaneous flash. So what we do is, in here you'll take the battery, and then we disconnect the flash out of the circuit. So physically what you have is something that looks like this. You have two switches going on here. So here's the symbol for your battery. And this could be like a little transistor battery that's 9 volts. You buy it, Radio Shack or whatever. You'll have a switch, and then you'll have a capacitor here. Then you'll have another switch, and then you'll have your flash bulb out here. All right? Now what happens here is we close this switch. This capacitor then charges up to whatever that voltage is, 9 volts. But the capacitor can have lots of charge on it. I mean, lots of charge. So now what you're doing is you're sitting there holding your camera, holding the button down, it's going, you'll see that little LED going on and off, and then it goes steady. When it goes steady, that's when this capacitor is charged up. So at this point, when you're holding the button down halfway down, that is completed. This is getting charged up. Then what you do, you open this circuit, close this circuit, and what happens? Kablooey. Now you're sending a tremendous amount of current out to the bulb, and what happens to the bulb? Poof. All right? Poof. Okay? Goes up in smoke. All right? So that's the idea here. So that gives me the nice flash that can, give me a nice little optical image that goes into my single lens reflex or whatever I got down here. All right? And that's the little flash capacitors are sitting right up in there. All right? I've actually, you wouldn't believe it, I have a cassette tape up here that this machine just ate, and I took, let me just go back here. I took these capacitors, now these guys that I had, I took them out of old TV sets. If you have old TV sets at home, don't go screwing around in there with a screwdriver, because these capacitors remain charged. You go in there and you short out those two terminals at the top. It's going to be just like my buddy when he was grabbing stuff on my desk. You can kill yourself. You can literally get killed because it's that much energy is hitting your body in that short amount of time. I took a whole bunch of these and I hooked one end of this up to a screwdriver and I hooked the other end up to another screwdriver and I brought those two contacts together. It gave out enough energy that it welded it. It literally welded the two pieces of metal. I have it on this tape, but the machine, when I got in here earlier, it ate my tape. So if I get the tape fixed, I'll show it to you on Wednesday, all right? But that's how much energy you can get out of these things, all right? All right, and again, a capacitor, you can look at it, again, it's just basically a separation of charge by a dielectric. You can think of fluid flow as pushing against a membrane, and then the membrane pushing back when you want to release it. The easiest way to think of a capacitor is, it's a balloon. You blow up the balloon. You're putting energy into the balloon. I take the balloon away at this point, I'm holding it, my balloon is nice and full, then when I let go, what happens?
Flies off.
It flies off. The energy gets dissipated in the form of motion. All right, so you're doing capacitors, you can store them up, just like blowing up a balloon, and then I can discharge it, okay? Another application is you may have these little microphones. Matter of fact, most of the ones that you have Oh, anybody have earbuds with the little microphones on the front? You got? Hey, oh, beautiful thing. What you got here? Does that have the microphone on it? Yeah, all right. In here is a microphone, all right? And that little guy right there, so you can talk on your phone, right? Isn't that cool, man? Yeah. All right, same thing. Temple Beat, East Carolina. Like the microphone, all right? There's a capacitive microphone right here, all right? The idea here is you speak into this little tube, all right? Well, that little tube, what it has is it has a little battery. There's a little battery in there, all right? Now, when you have to plug yours into your phone. That's where you're getting that power from. There's one parallel plate here. Now, this end of the battery is connected to this plate, so this is all positively charged here. The negative end is connected to this plate, all right? To this plate right here. Now, the thing is, what's going to happen is as you speak, this plate's going to start moving in and out. Now, remember, capacitance it's the separation of the two plates. So what I'm going to do now is as I talk, one plate's going to start vibrating. It will then put out a current out here that mimics my voice. It's almost the same thing. So when I start talking, you deform the plate. You will then get a current that will flow out of this circuit into whatever you're talking to. All right, your phone, to a recording, or it could be to you. All right, that's how that thing works. Now I messed up this slide. This should be, when it comes back the other way, the current actually reverses. So I'll fix this part of that slide for you. This is what we call the compression. Then there's the refraction stage on that capacitive microphone. Okay? All right. Now the mathematics comes. We've had our entertainment. All right. Capacitance is given by, the Q is the charge on the plates, C is the capacitance, and V is the voltage. All right. The capacitance itself, this guy C, is defined by this epsilon, which is the material, the dielectric that sits in between them, times the cross-sectional area of the plate divided by the distance that separates the two plates. All right. So that's basically how it works. You're not going to do any capacitance calculations in here. Don't worry about it. We're just going to be using it as a mathematical method. So epsilon is the permittivity, A is the surface area, D is the distance, and we measure these are farads or picofarads if it's 10 to the minus 12th, nanofarads if it's 10 to the minus 9th, and microfarads is 10 to the minus 6th. Okay? You're going to hear this name farad a lot. We named this device after a guy by the name of Michael Faraday. All right? He's the guy that does a lot of electromagnetism stuff, so we'll come back. That's the symbol for a capacitor, just as I put up here on the board. It's just two parallel plates with a current I coming in and a voltage V across it. All right. Oh, there's that damn thing. There's that four-letter word right there. All right? So we're going to work on this. All right? We'll show you where these relationships come from. First, you start off with the current voltage relationship for a capacitor is C dV dt. I then divide through by C. We then integrate both sides. So here's what we're doing. So the relationship that we start off with, let me just get this right for you, I of t is C dV. Now, I left off the implicit assumption that everything is time-based here, but that's what it means. Where you see V, it's V of t. Where you see I, it's I of t. The current in the circuit is going to change as a function of time. And the voltage in the circuit is going to change as a function of time. Okay? So now what we have is, what we want to do is we want to solve for this voltage V. So here what we do is we take I of t and divide it by the capacitance, so that leaves the left-hand side. Okay? Is that okay with everybody? That's all I did is an algebraic manipulation here. Now what I'm going to do is, we're going to do this. I'm going to multiply both sides by dt. Is that okay? So therefore, goodbye, that goes there. And that just hooked me there. So now what I'm going to do is we can write this as I of t dt 1 over c is equal to dv of t. And now we're going to bring in that little magic piece that's called the integration. We're going to integrate both sides. Integrate from 0 to t. The right-hand side is what we call a perfect integral, all right? All this is we now have, instead of dv of t, what pops out of here is v of t minus v at 0. The left-hand side remains the same. So what we're left with here is 1 over c, the integral of I of t dt, plus v at 0 is equal to v of t. Now, enough of the mathematics. Let's sit back and just, what are we doing here? If I give you, how did I get all the way back there? All right. What we're saying here is that if I give you the current through a capacitor, mathematically I can calculate the voltage across the capacitor through this integration here. And that's what we're going to do. We're going to do a couple problems. I'm just going to say, you know what? Let me go forward here. Having fun. All right. We had just derived this relationship over here where T0 is just, I used it as 0 over here. Okay? We can do the same thing for the charge. But all we're going to worry about is voltage and current. Don't worry about the charge for now. All right? All right, so we went through and we did this integration, and we came up with this solution down here, which is exactly what we have over here. So if I now tell you what the current is in a capacitor and the initial voltage across a capacitor, you can then tell me what the voltage is going to be for all time. All right? For all time. So here we have, again, the capacitance. Now you may ask, the capacitor, in this application that we had over here, was the capacitor charging or discharging? It was charging at first, and then what happened? It discharged. So it does both. You charge it up, and then you can discharge it. You're basically storing the energy there until you're ready to release it when I throw that other switch. So we can have current can come into the positive terminal, which means it's charging, and when current goes out of the positive terminal, it's discharging. So, and again, all we're going to worry about, these are the two relationships that we need. All I'm going to do for the next 2 days is exercise these two terms right here. That's it. And we're going to use the integrals that we had originally up, the integral of sine of AT, cosine of BT, and e to the minus CT. All right? We're going to use them. All right, so let's say I have a capacitor. This is what I'm showing you on the left here. Have you guys seen this yet? Independent current source? Have you done any electric circuits yet? Talk to me. None. All right, so you haven't really, all right, okay. You got to tell me this. I mean, because I just saw, like, what the hell's that? All right? Tell me. Like, hey, Doc, where, all right. What this is an independent current source. It's just like a battery. It can produce a constant current or some time-varying current. You know what's a good current source? You're staring at one right over there. There's an outlet. There's an outlet. What comes out of those outlets?
120 volts AC.
120 volts AC at how much current? Depends on what the load is. But it usually, there's a breaker in there that usually goes up to 15 amps. So it can go up to like 15 amps. But we can think of this as an independent current source. Now what we're going to do here is we're going to say, okay, the current source, this current source, the current coming out of this thing is 6 sine of 4t. It could be 6 sine of 377T, which would be 377T is 60 hertz. But right now we're just going to use this mathematical expression. 6 sine 4T is the current flowing into that capacitor. So now I is now known. I is known. What we want to find out is what's the voltage that's going to be across those two terminals right there. All right? What's going to be that voltage? And we say that the initial voltage, the capacitor was initially charged and had 1 volt sitting on it. All right, so now here's what we do. We go back to this expression. What is I of t here? It's 6 sine 4t dt plus the 1 volt. All right, let's integrate this out. Somebody help me out here. Integrate sine 6t, sine 4t times 6. What do we do with the 6? The 6 can be pulled outside, right? So here's what we're doing. We're integrating now we get to the mathematics part. So we're integrating here zero to t sine 6t. Now again, this capacitor is a 2 farad capacitor. That's where the 1/2 comes from here. All right. So I've got 6 sine of 4t dt. Let's go back to our integral of sine of at dt. What was that integration again? Minus a cosine of at. All right, now for this integration, we have the 6 comes out in front. So I have 6/2 integral from 0 to t sine 4t dt. All right? So now what do we have? What is a in this case? 4. So now I'm going to have, this is going to be 6/2 times the 4 times the sine of 4t evaluated between 0 and t. Okay?
Cosine? Or negative cosine now?
Or cosine, I'm sorry. Yeah. So I'm going to bring the minus sign all the way out here, cosine of 4t. And now I evaluate this. So this is, so here I've got, this is going to be minus 12, right? Cosine, now I have to evaluate the cosine between the lower and upper limit. So this is going to be the cosine of 4 times t minus the cosine of 0 times t. Everybody with me? Okay? And now, oh, I forgot to add the 1 on here for the V0. That's the 1 volt. We okay so far? All right. So that's we evaluate this guy. All right. Wait a minute, 3/4. Whoa! Whoa! Somebody gave me bad advice here. What's the integral of the sine of AT? 1/A. I was waiting for somebody. 1/A. So this is 1/4. This is 1/4. This is not 12. This is 1/4. And the same thing with the cosine. It's 1/A. So it's, let's see. So here we got, what do we got? So it's 3/4. All right. Okay? And we have the +1 here. Now, if you notice, we have, so this is V of t. So now this is equal to minus 3/4 cosine 4t. Then we're going to have, bring in minus 3/4 inside here. Cosine of 0 is 1. Okay? So this is going to be plus 3/4 plus 1. And that's where we get that. Okay? Talk to me. Question? Yeah, go ahead.
Why
Okay, when you do an integral between the two limits, all right, I got the integral of, this is, what were we doing, sine? Or let me, all right, hold on, let me do this. These are what we call definite integrals, okay, because they have definite limits, the lower limit and the upper limit, okay? So when I have from 0 to t of, in this case it was sine, let me just use AT, all right? What you do is this integration is equal to minus 1 over a, all right? Now, the integral itself is going to give me the cosine of AT, and then you have to evaluate that integral between the lower limit and the upper limit. And that's where I get 0 to t here. And then inside, this is equal to minus 1 over a cosine. You put in the upper limit first. So this will be AT minus the cosine of a times, and that's the lower limit. So that's a 0. And that's where you get that from. You're evaluating, good question. You're evaluating what are called definite integrals. There's also indefinite integrals that we just add on a constant, but that's how it goes, all right? Does that answer your question? Okay, yeah.
And you're plugging in T and 0 there?
Yeah.
Are you just supposed to plug it in for T?
Oh, yeah. Well, this is 4 times 0, and the other one was, this should be 4, thank you, yeah. This should be 4 times 0, thank you. I'm getting a little sloppy, but it's okay. No, it's not okay, really. Yeah.
So, on the third line, you have the, you have the square bracket to get that line.
That line is the same thing as evaluating. Sometimes I use them as square brackets. Sometimes you use it as the line. Yeah, it's notation, but it's important to get it right. This means when you see he's right, he's saying, "Yo, Doc, what's the difference between this and what's the difference between that?" They're the same thing. Okay, they're the same thing. You get my drift? All right. Good questions. Good questions. Keep me on my toes. All right, where did I do with my clicker? Is it up here? You see me in class, stuff flies all over the place, man. I don't know how I keep it together. No, I know how I keep it together. What keeps America together?
Duct tape.
Duct tape. That's it. What else keeps America together? Bubble gum and bobby pins. All right. All right. Let's do another one. All right. So here we have now we're going to apply, the voltage waveform is applied to a 30 microfarad capacitor. So now I have, this is a voltage, this is a battery or what we call an independent voltage source. That's my capacitor right there, all right? I'm now going to make this voltage source start at 0, then go up to 10 volts in 2 seconds. And then I'm going to have the voltage source stay at 10 volts for, I think, 2 more seconds to 4. Then we're going to have the voltage source start dropping down and going negative down to here, then constant, and then back up to 0 again. This is where I'm just sending a signal into this capacitor, a time-varying signal, all right? So V of t is time-varying. Now, let me ask you a question here. I now have, and let's just think about this before we get into all the mathematics here. All right, so what we're doing is we have a voltage source, and we're sending that into this capacitor. So here's my capacitor. This voltage source is positive. What's going to happen to the capacitor from 0 to 2 seconds? Is it going to charge or discharge? It's going to start charging. Positive current's coming into it. It's going to start just like we did over there with the flash bulb. It's going to start charging up. So now what's going to happen is we're going to look at this is what we need to do is find the current. So now what we're going to look at is the current through a capacitor is equal to C dV of T dt. Now, what is the derivative in physical plane words? Can you talk to me? What is a derivative? It's a change in slope. Let's not do any mathematics. Let's just draw what the current's going to look like from that figure there. Let's just draw it. So here we have the voltage goes up, flat, down, flat, back up to here. So this is V of T. What is the slope doing from 0 to 2 seconds? It's increasing. Is it increasing quadratically, exponentially, or it's linear? So the derivative of a constant slope is what? Is a constant number. Okay? So so the current is the capacitance times the rate of change of voltage. So if I take the derivative of this here, what do I get? I get a number, right? I get a number. So the current, I of t, is going to be a constant number. Now, I get into this interval here where the slope is fixed. There is no slope, is there? It's constant. What's the derivative of that? What's the slope of that? 0. So I automatically know that the current is now going to be 0. I go over to here from 4 seconds to, I think it's 6 seconds. The slope's going down. And it's linear. The derivative of that is a number. So it's going to give me something down here. And it's going to be a negative number. Why? The slope's negative. Slope is negative. Is the slope still negative here? So it's going to stay like this until this point. What happens when I hit this point here? It goes back up to 0. And then what happens? It goes back up. So this green curve, without me doing any integration, differentiation, or whatever, gives me an idea of what's happening to this capacitor. The capacitor is charging. The capacitor now remains fixed. The current is 0. What's happening to the capacitor at this point right here? It's discharging. What's happening here? Nothing. What's happening here? Charging again. So you got charge, constant, discharge, nothing, there. So I don't even have to get into the old grinding away the numbers yet, because I can look over there and say, you know what, my answer better look something like that, because that makes sense to me. That physical capacitor is going to do that. It's going to make sense to me. Charge, don't do anything. Discharge, don't do anything, then charge again. So I know that my current relationship in the end has to look like something. So here we have, now if we get into the little math here, the capacitor is a 30 microfarad capacitor. That's where we get 30 times 10 to the minus 6. And C dV dt is the slope of the waveform. So we just go in. For 0 is less than t, which is less than 2, dV dt is 10, which is this value here, over this 2 times 10 to the minus 3. So therefore, the current during this time period is going to be 150 milliamps. So that's what this number right here is going to be. 150 milliamps, or 0.1 amps, 0.15 amps. All right? And that's what it's going to look like. And guess what? What we have there is what we have over there. All right? So again, that makes sense. So now we just do the same thing for 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. All right? Capiche? Capiche. Nastrovia? Nastrovia? Comprende? Comprende. All right. Gin Don? It's a little drinky poo. All right. Let's take a break for a minute, because I can see the eyes are glazing over. I'm going to show you a little application here. We're going to get to, now I'll do these. You may remember from physics, if you had physics in high school, if I put current through a wire, let's just assume I have a wire here, and I have a little piece of paper with some iron shavings on this thing. I put a current through that wire, what happens to these iron shavings? They start moving. You got a magnetic field produced around that wire. Current through a wire produces a magnetic field. Yeah. It would heat up too if you put a lot of current through it. Yeah. It would heat up because there's resistance in there. There's resistance in it. Yeah. It will definitely heat up. But let's just, right now, these randomly placed iron shavings will then have a pattern of almost a circular pattern around it. That changed the world. That right there. That simple movement of current through a wire, and people noticed a magnetic field around a wire, changed the world in a dramatic way. Because now what I can do is I can have one end of this wire sitting in England or Ireland. The other end of this wire can be sitting off Cape Cod. All I have to have is a guy sitting in Cape Cod sending current all the way through that wire. They had batteries the size of this room for those telegraphs. Amazing. And all I need at the other end is a little, as soon as current comes over here, if I have a piece of metal sitting here, what's it going to want to do to that wire? Bam! It wants to go right to it. So now if somebody on one end in Dublin turns the current on, and I have sitting over here a little piece of metal, bam! It hits it, guess what? However they touched on that switch in Dublin now comes to me in Cape Cod. And if I now start to do, if I hold the button down for, let's say, 2 seconds, that creates what we call a dash. If I hit it real quick, that creates a dot. So I'm going to be sitting at the other end here, and it's what is that? If I know what that code is, I can communicate with the guy 6,000 miles away. You've now established the first internet. I mean, that's it. Just send me some dots and dashes. Well, now we send all kinds of nice things over the internet. Not just dots and dashes, but you know what I mean? But the idea here is, let me just show you a quick video of this concept. All right, we got two minutes left, gang. Don't disappear on me here. All right. All right, what I have here, let me just hold off on this. There's an electromagnetic coil that sits right here. What I'm going to do is I'm going to get an object and I'm going to have it float in the thin air. It's just going to float. There's a magnetic field produced around this guy. You can see it floating by itself. You got mg coming down, and you got a force coming up that's due to the magnetic field. And they're perfectly balanced. Still sits there. All the capacitors and all the electronics are down there. Gang, it was a pleasure meeting you the first day. I'll see you on Wednesday.